In this video, we're taking a look at how registers and counters can be specified in Verilog. We will look at D flip-flops, at registers with n bits, shift registers, and we will also explore the possibilities of having an enable so that counters or shift registers can be either enabled or disabled and are not reacting to clock inputs when they are disabled. As a first example, we will look at the basic n-bit register. And the Verilog code for that looks like this. We have a parameter n here that we specify to be n equal to 16 so that we can have a register of arbitrary size. Then there is a D input, there is a Q output, and of course both of those have to be specified such that they grow with that parameter n. So we make here vectors of length n by saying we go from n minus 1 down to 0 for both the D and the Q. Then there is a clock input and there is a clear input. And the clear input, there is this underbar at the end of the clear input indicating that it's active low input or negative logic. So we have here the sensitivity list, neg edge clear and pos edge clock. So when there is a negative edge at the clear input, we are clearing the registers through this command here. And that is going to be asynchronous because it will happen whenever clear goes low. And then the main control here in terms of the timing edge is the clock, which occurs on the positive edge. So it's a positive edge triggered register. And the data D is stored in Q whenever the clear is high and when there is a negative to positive transition on the clock. If you want to be able to load a D flip-flop with different kind of data, then it's useful to have a structure where we have a multiplexer at the input. So if we look at this here, we could have a D flip-flop with an input D, and then we have a multiplexer where we can choose whether D0 or D1 is being read into the flip-flop at the time when the clock is happening. So in this particular case, we have a positive edge triggered flip-flop here. And then there is a select input. If that select input is equal to 1, then we choose the data input 1, D1, into Q. And if select is 0, then we choose D0 to go into Q. So in this way, we are able to select between the data inputs. And if we make, for example, a shift register, we can use one of the inputs to shift from one flip-flop to the next, and the other input could be used to actually preload the shift register. An alternative way to specify this would be to specify an auxiliary wire here, D, and then use a continuous assignment to D using the conditional operator here. So this construction here, so this is called the conditional operator. So we assign to D a value that depends on what the value of select is. So that's the variable here with the question mark after it, that is the selector. And then comes the first variable, that's the one which is chosen when the select criterion is 1 or true. And the second one after the colon here is the one that is chosen when the selection criterion is 0 or false. So in this particular case, when select is high, we choose the D to be equal to D1. When select is low, then D becomes D0. And then at the positive edge of the clock here, so this is positive edge triggered. At the positive edge of the clock, we then read D into Q of the flip-flop, and that gets stored then in the flip-flop. The next example that we're taking a look at is a 4-bit shift register. It is hard-coded, so it doesn't have a parameter here. We set directly both Q and R as 4-bit vectors that go with indexes from 3 to 0. R is the data input for loading, and Q is the output. Then the variable L here goes high when we load the shift register. W is the input that goes into the serial portion of that shift register, and clock is the clock for clocking it. We have an asynchronous load here because we have two edge statements here, both positive edge in this case, one based on L and the other one based on clock. So whenever L is going high, we will enter the always block, or when the clock is going high, we also enter the always block. And then inside the block, we check first whether it is L or not. If it is L, then we set Q equal to R. So here we set, or let's say we load Q with R. And if it's not load, then it must have come from the positive edge of the clock. And then we start the shifting operation here. We have W, which is the data that comes in, that goes into Q3, and then Q3 goes into Q2, Q2 into Q1, Q1 into Q0. So we create this chain here of the shift register entering at the Q with the highest index and going all the way down to the Q with the lowest index. We would like to parameterize this, and so we put in a parameter n equal to 8 statement in here that can be changed to any other value that we need. And now our input R and the output Q are both growing with the size of this parameter n. L, W, and clock have the same functions as before. And to implement this whole thing, we use a for loop down here. And in order to control this for loop, we need a loop variable. So that's this integer I here, that's the loop variable. And in this particular case, we have chosen to make a synchronous load, so we only have the positive edge of the clock in the sensitivity list of that always block. And whenever that transition of the clock is happening, then we check first whether it's a load, and if it is a load, we load Q with R, and if it's not a load, then we do the shift operation, which is implemented here as a for loop. So we go from Qi plus 1 to Qi for I going from 0 up to n minus 2. It's less than n minus 1. And then the last one, the Qn minus 1, into this one we are reading W, which is the data input that comes from the outside into the shift register. An alternative way to implement an n-bit shift register is to use the generate block, as we have done here. So this is a hierarchical way of implementing things. We have this shift n on the bar gen module, and that module makes use of the mux DFF module. That's the D flip-flop with a multiplexer at the input. And we instantiate this mux DFF as many times as is needed in order to make an n-bit shift register. And in fact, the number of times we do have to instantiate that is n times. We do n minus 1 times here, n minus 1 instantiation. And then there is an additional one. Okay, so here is one more. And this one is different from the others because it has the W, the input into the shift register in it, whereas all the others are being fed from the previous stage in the shift register. So here we go, for example, Qi plus 1 is going to be fed into Qi. If L is low and if L is high, then Ri is going to go into Qi using that MUX-DFF module. So in this way, we can split things up into a top-level module and then some submodules that are being instantiated from the top-level module and could be reused, for example, in some other kind of context. Now let's take a look at some counters. We start again with something simple. This is a 4-bit up counter. So the module is called upCount4. It has a clear input. Again, this is an active low clear. Then a clock input, an enable input, and a Q output. It is hard set to a size of 4 here. And we are using an asynchronous clear because we use the neg-edge clear as one of the parameters in the sensitivity list. It's also positive edge triggered on the clock through that portion of the sensitivity list. And we check first whether it is clear or not when we get into the always block. If the clear command has been asserted, then Q is set to 0. Otherwise, we check if the enable is active high. And if the enable is active high, Q becomes Q plus 1. If enable is low, then nothing is done, and the value of Q just stays the same as it was before. So it is frozen if enable is equal to 0. Here is a parameterized version of an n-bit up counter with enable, load, and clear. So the parameter n is given here at the beginning. As before, we are making R and Q dependent on that parameter n. And then we have the clear input, the clock input, enable input, and in addition now also the load input so that we can preset the value of the counter. So it's an asynchronous clear because we have a separate statement here for the clear and for the clock in the sensitivity list of the always block. It's positive edge triggered on the clock. If clear is 0, then Q is set to 0. And otherwise, if clear is 1, then we check if it is load. If load is set, then we load the value R into Q. And if it's neither clear nor load, then we check as a next thing whether the enable is set high. And if the enable is set high, then we are going to count up by adding 1 to Q. Note that the load here is synchronous because we don't have L in the sensitivity list. So L is going the always block is being entered when clear goes low, but then that is immediately caught by that first if statement, so it cannot go into the L statement. However, if the always block was triggered through the positive edge of the clock, then that will go past the clear, and it will then check whether L is high or not, and it will only go into the actual increment of the count if L has not been set. So this results in a synchronous load from the register R on the positive edges of the clock. Another variation of the counter is to have a counter that can count both up and down. So here we look at the up-down count n module. So it is parameterized with the parameter n. We can load it again with the value R. we can clear it. We have an enable input, and we have now also a select input where we can select whether we count up or down. The output register as well as R here are both dependent on n, so we make vectors of size n for those two. Here we have chosen to use an asynchronous clear again, and we have the positive edge of the clock, so it's positive edge triggered. We use the same construction as before. We check first whether a clear command has been issued, and if it is, then we set Q to 0. If not, then we check whether it's a load, and if the load is present, then a Q gets loaded from the input R. And if none of those is true, then we check the enable, and if enable is 1, then we do enable the counting. Now the interesting thing here is the choosing between up and down. We use here the conditional operator again. Okay, and you can see that the condition that we are looking at is up-down. So that's the selector, whether we count up or down. If up-down is equal to 1, then we choose a 1 here for what's being added to Q. And so we increment the count. So up-down equal to 1 means up. And the second one here, if up-down is 0, then we choose -1 to be added to Q, so that if this is equal to -1, that means that we count down. Okay, so this is kind of a nice construction to make it go either up or down. Of course, we could also have used an if statement, but this looks a little bit more elegant than that. We have already used enable inputs on the counters. We can also use that in general in any kind of flip-flops that we have in circuitry. And it is useful to have control over when a flip-flop is reacting to a specific clock edge or when it is not reacting. An example would be if we make a 2-digit BCD counter, then we could make 2 modules for counting up 0, 1, 2, up to 9, and then back to 0 again. And then the ones part of the counter would have to count on each positive or negative clock edge, but the tens counter would only count on each tens of the clock edges. And so we would then want to be able to disable the reaction of the tens counter, so that it only counts every 10th clock, and the other 9, it is not joining in on incrementing when the clock is happening. So one idea that one could pursue to enable or disable a D flip-flop is through enabling or disabling here whether the clock goes through to the clock input or not. Okay, that looks relatively simple. We just have to put in an AND gate and have that enable input. But it turns out that that can lead to problems, because we could, for example, generate additional edges through that. If the clock is high and the enable goes low and then back high again, that would create an edge, a positive edge here that goes into the counter and makes it count 1 too many times. So this is usually not being implemented that way. We usually prefer to have a solution that looks like this, where we control the D input rather than the clock input in order to enable or disable the changes in the state of the flip-flop. So the way this works here is that when enable is 0, then we have the loop closed around here, like this. So this is for enable equal to 0. And so the data just remains at the value that it was in the Q, in the D flip-flop. And when enable goes high, then So if this goes high, then we would go through the D input and go through the D input of the multiplexer, and that gets passed on then to the D input of the D flip-flop, and the D flip-flop will then read in whatever the D value is at the input of the multiplexer on the next positive edge of the clock. So this is a much more elegant solution, and it will lead to much fewer problems than the other one where we would try to control the clock. So here is Verilog code for D flip-flop with enable. As usual for D flip-flops, we have a D input, we have a Q output, we do have a clock input, we have a clear input so that we can clear it to 1 at the beginning, and we also have the enable input. So everything here is just 1 bit. We just have one D flip-flop here. We have a asynchronous clear here through the neg edge of the clear underbar. It's active low. And we have positive edge triggering on the clock. And then we just have here, if the clear is equal to 0, then we set Q to 0. But otherwise, if clear is not down to 0, if clear is equal to 1, then we check whether the enable is high. If it is high, then Q will be set to D. And otherwise, we just leave the Q value in the register, because Q here is defined as a registered variable. It will retain the value of Q if the when the if command here is not true and there is no else clause for it, it will just simply retain whatever value it had before. We can extend this idea of the D flip-flop to an n-bit register, and that's being done here. So we have the parameter n equal to 8, so that we can have an arbitrary size. R, the input, instead of the D, is now variable in terms of n, and Q is variable in terms of n. Then we have again a clock, a clear, and an enable. We have an asynchronous clear here, a positive edge triggered here. Okay, so let's go here. So this positive edge triggered. And we, as usual, we ask first whether clear is equal to 0. If clear is not, and if clear is equal to 0, we set Q to 0. Otherwise, we check whether enable is set high. And if enable is set high, then Q becomes R. In this case, it's now a transaction that involves n bits rather than just 1 bit in the D flip-flop. And if enable is low, then Q just remains at the value that it had before. The idea, of course, can easily be extended to now using on an n-bit shift register with an enable. We have again the parameter n here, so it's usable for any size of shift register that we would like to have. R and Q are dependent on this n. We have the input L for load, En for enable, W, that's the serial data input into the shift register, and clock for clocking the whole thing. In this case, we have a synchronous load, and we load this synchronously with R if L is high. So L is the load command. When L is high at the positive edge of the clock, then we set Q equal to the input, to the data input R. That's a parallel load. And if that is not the case, then we look at the enable signal. And if the enable signal is high, then we do our shift. We shift W into Qn minus 1, and then Qn minus 1 goes into Qn minus 2, and so forth. So we have this chain of actions here. We go with W into the Q with the highest index, and that goes into the Q with the next lowest index, and so forth, all the way down to 0. And in this way, we implement the shift command, but only if enable is high.